Click the bell icon to get latest videos from Ekeeda.
Hello friends, in this particular video, in today's session, we will learn log and anti-log amplifier using operational amplifier 741. First of all, very first question comes in your mind that why log and why anti-log amplifier is required for analog and digital circuit. So we should know the advantages of log function. What that log function is. Let us try to catch some values of log. Let us say that log of 1. Log of 1 is equal to 0, right? Then we will jump for log of 10, which is equal to 1. Then we will jump for log of 100, which is equal to 2. Then log of 1000, which is equal to 3. And likewise, if we take log of 10 to the power n is equal to n. Now, you know why I am calculating all this stuff? Because the very first advantage is log is a perfect dynamic compression factor. If I am taking this value as x, let us say that this is in a tabular format. Let us say that this is in a tabular format, and I will slice this part as log of x and f of x. F of x is equal to log of x, and if we try to plot the value of x with respect to f of x, then we will come to know that if I have the difference between x is 10 minus 1 is 9, then we are getting the difference between fx2 values is 1 minus 0 is 1. That means I'm compressing the value x, which is 10 minus 1 is equal to 9, as 1 minus 0 is equal to 1. Similarly, 100 minus 10 is 90, and this 90 is getting converted into 2 minus 1 is equal to 1. That means this fx is actually a compressed version of x, and that is done by log function. Understood what I am trying to give you input as? Log is a perfect compression factor. That means if I have the input or any voltage which is in the range of 100 volts or any 10 volts, and I want to compress that with dynamic compression, then we can reduce that particular value with this particular log function. Then question arises next, how can we implement this log amplifier? And then next question arises in your mind that how we can implement this log amplifier using operational amplifier. The very basic fundamental of diode is very useful in this particular circuit. Concept is with diode, right? Now with diode, I can say that first of all we'll have to learn what is the equation of current flowing through diode. Equation of current that is nothing but IF is equal to IS multiplied by e to the power Vd divided by Vt. Let us learn one by one terms. What is IF? IF is nothing but forward current. IF is nothing but forward current. IS is nothing but reverse saturation current. which is in the form of nanoampere or picoampere, which is very, very less. This is in the form of milliampere. Vd is diode potential. Junction potential, we can also say that. So another namakaran will be junction potential. And Vt is your thermal voltage. Now if you look at this particular expression, this is in the form of e to the power something, and its inverse is nothing but logarithmic. Log to the base e. Log to the base e I can easily convert it into log to the base 10 very easily with a mathematical expression. Now our job is to use diode such that the circuit will look like as the log amplifier. That means your output voltage should be in the form of log of input voltage multiplied by constant value. Now I will draw the simple basic log amplifier using diode configuration. This is the input resistance R1. Here I am giving the input V1. This input V1 is applied to inverting terminal of operational amplifier. Non-inverting terminal is connected to ground through offset resistance ROM. Here I am applying diode instead of resistance RF. Negative, positive, this is plus VCC, this is minus VEE, and here I will be getting the value of output that should be in the form of log of input voltage. So I will roughly specify this as, let us say, A into log of B into V1. BA can be anything in the form of constant value. Now to get this particular expression, we will start with the simple KCL and virtual ground concept. Here we are getting the virtual ground concept as we are getting in inverting configuration amplifier. This is inverting amplifier itself. Just I have replaced the resistance RF by diode. This is positive, this is negative, and here we are having the value Vd. Consider that this node is node number A. We will apply KCL at node A. Using virtual ground concept, initially we consider that VA is equal to 0 volt. Okay, and we can say with application of KCL, we are getting input current, that is nothing but V1 divided by R1 directly, V1 minus 0, V1 divided by R1, and that should be equal to outgoing current, that is nothing but the current flowing through this diode, right? We can say this is equal to current flowing through this diode is nothing but Is multiplied by e to the power Vd. Now what is Vd? Let's treat this as Vd itself, Vd divided by Vt. Understood? This is nothing but the current flowing through diode. Current through diode. More specifically, we will write this as forward current. Okay. Now we will discuss what is Vd. Vd is equal to. Now this is your forward current through diode. So well, what is the value of Vd? The value of Vd we'll have to calculate. This plus is connected to Va, which is 0, and this is connected to VO, so I can say that VD is equal to 0 minus VO. We will incorporate this VD value is equal to minus of VO, then we can easily get the relation between VO and V1 and all are constant. We will put the value V1 divided by R1 is equal to IS into e to the power, instead of VD I will write minus VO divided by VT. This will become V1 divided by IS into R1 is equal to e to the power minus VO divided by VT. We'll take this e at the left hand side, so it will become ln. Ln means log to the base e. V1 divided by IS into R1 is equal to minus of VO divided by VT. Very simple. So we will be getting the value VT into ln multiplied by IS and R1 is equal to VO with negative sign. Now here I will be getting that the output voltage is in the form of log of input voltage, and that is why this is the expression which gives you the effect of log amplification, that means compression. Now what is the difficulty in this particular circuit? First of all, problems in diode. The diode is a discrete circuit, right? So this is your discrete device. If I want system on chip, everything should be on chip, then I can form transistor on chip, but I cannot form diode on chip, right? So what we can do the system in such a way that we can form a circuit in such a way that I will replace the diode with your transistor by having one short circuit connection, such that this transistor will altogether act as a diode itself, and operation will act as only log amplification, right? So this can be achieved as one more thing is this discrete device, and due to the fact that problem in fabrication of such device is not possible with less area. So to reduce the area, as we are moving towards the integrated era, and that is why we are neglecting the diode, we are using transistor instead of diode. Rest all the circuit will be same. So we will learn how to design log amplifier using transistor BJT. We will draw circuit R1, this is V1. Here I will form a transistor. I will keep this all the terminals as it is. Now very crucial part is which terminal should be collector, which terminal should be emitter, and which terminal should be base, at what particular potential it should be connected. First of all, I want this completely as a diode circuit, as a diode, but because this diode is a discrete device, and that is why we are moving towards a transistor. To increase the stability and to reduce the area, to reduce the power consumption as well. This is positive, this is negative, and this diode configuration we will be getting in B to E, and that is why we are using VB is equal to 0.7. So what we can do, we can take this as emitter terminal and this as base terminal, such that we will be getting the value of VBE as a positive value, same as that of your VD. We will apply this ground and we will apply emitter to this terminal. Now if you look at this particular terminal and this particular terminal carefully, collector is altogether grounded by using virtual ground concept, and base as well grounded. That means collector and base is already shorted. So actually this three terminal transistor is getting converted into diode of two terminal diode, and that is why we are using this kind of circuitry to get log amplifier. Let's proceed further. If we are getting this kind of configuration, then we will be getting VBE instead of VD, and rest all the values mathematical expression will be same as that of your diode log amplifier. Understanding the concept behind the structure of this transistor is very important. Rest all mathematical expression is same as that of your value of VO in the form of logarithmic V1. So your expression will be VO is equal to Vt multiplied by ln of V1 divided by Is multiplied by R1. Now problem here is with minus sign. VO, now VO will become minus of Vt ln V1 divided by Is into R1. Now the problem here is with respect to Is, right? This Is is minority charge carrier current. And Is multiplied by R1, we will take this as V reference voltage. If we take this Is multiplied by R1 as V reference voltage, I cannot keep this V reference voltage is equal to constant value, and this is because minority charge carrier current is changing with respect to temperature. If temperature changes, this minority charge carrier current can change and will lead to change the value of VREF, and that is why this VO will not be as a function of only V1, rather than that it will be as a function of VREF that will act as a variable, and I don't want that mess up. I want VREF should be constant value, and for that we have to do some another circuitry arrangement such that I will be getting VO is with temperature stable. This is our log amplifier, and this is the extra structure to avoid that mess with Is dependency on temperature. The value here that we will be getting is, let's say, VO1, and the value that we will be getting over here is VO2. Within short span of time you will get to know that why I am adding this extra circuit with input as V reference. Now considering the fact that this is Q1 and this is Q2 having the transistor of same family, so I will be getting, let's say, the value VO1 is equal to Vt, rather minus Vt, multiplied by ln of V1 divided by Is into R1. Let us treat this resistance as R1, this as well R1, this is ROM, this is ROM. Now tell me what will be the value of this VO2. VO2 is equal to minus of VT ln of, instead of V1 we will be getting VREF, that is DC value, constant value, VREF divided by Is into R1. Right? We fed these two inputs to differential amplifier. This is negative, this is positive, and if all the resistances value is same, let's say R and R, this will give you the output which is in the form of VO2 minus VO1. So whatever value VO I will be getting, that will be in the form of VO2 minus VO1. Let's check that whether we are getting that VO2 minus VO1 is exactly the log function that we have got earlier with diode and single transistor amplifier. We will express this VO is equal to VO2 minus VO1. What is VO2? VO2 is nothing but minus of VT ln of VREF divided by Is into R1. What is VO1? VO1 is minus of VT, so minus minus will become plus, plus of VT ln of V1 divided by Is into R1. Now here I will take this VT common, VT common, we will be getting ln of V1 divided by Is into R1 minus ln of VREF divided by Is into R1. Now, if you have learned the log properties, we can get to know that the value of internal bracket will get split up into ln of V1 minus ln of Is into R1 minus ln of VREF, right? ln of VREF, minus of minus will become plus ln of Is into R1. Now the beauty of this particular circuitry is that I'm not getting the value of Is into our formula, so this is somewhat temperature independent circuit. So I can say the value we are getting is Vt ln V1 minus ln of VREF, that will give you the value ln V1 upon VREF. Now what is missing over here? Missing over here is nothing but minus sign, and that negative sign we can easily include by adding your inverting buffer circuit, right? Here negative sign is missing, right? And that can be get by adding inverting buffer circuit. So let us treat this as your output VO, and which is equal to Vt into ln of V1 divided by Vref that I am giving as input for my buffer circuit, which is giving me just the inverted output. If R and R both are same, the value of VO dash will become minus of Vt into ln of V1 divided by Vref. Now here I did avoid the temperature dependency in the form of this expression. So I can get the logarithmic amplifier perfectly with these three stages. First is your log amplifier with transistor with V1 as input. Second is log amplifier with transistor as well, but VREF DC value input voltage. And the third stage is your buffer circuit and differential amplifier. So this 4 op amp will give you exact log amplifier, which gives you the value VO dash is equal to minus Vt ln of V1 divided by Vref. Now only one question is unanswered. Can we convert this ln into log? Because ln is nothing but log to the base e, and log is nothing but log to the base 10. Okay, we can easily convert by mathematical expression very easily. Log of x divided by log of e, that we will be getting log of x to the base 10. Okay, this is a mathematical expression to convert this. This is very easy, not a circuital point of view. Now we will jump into your anti-log part of amplifier. Once we are thorough with log amplifier, it is very easy to convert this into anti-log amplifier. Now we know the diode, transistor and the temperature dependency factor in your log amplifier. Exactly same situation, just we will change the orientation placement of the diode and the transistor. We will be getting the anti-log amplifier. Let us see. This is nothing but inverse of log. Now inverse of log is also in the form of 10 to the power something or e to the power something if log is base to n or e respectively. So we will be getting the expression in the form of exponential nature. So e to the power something, that should be our expression of the output voltage with respect to input voltage. We will draw this circuitry over here. Now instead of the feedback transistor, feedback diode, we will apply diode and transistor at the input only. So here we will apply the diode over here, and here we will apply a simple resistance at RF. Now you will get to know that why I said that just the placement change karo and you will be getting the value. Instead of log amplifier, you will be getting anti-log amplifier. This is V1 plus minus, this is Vd. If you change the orientation, nothing will happen, just plus का minus हो जाएगा, minus का plus हो जाएगा, nothing else. Now we'll just do the application of KCL over here. If you apply KCL at node A, you will be getting V1 here. I will be getting V1 minus VA is equal to VD, right? But from virtual ground concept, we are getting VA is equal to 0. So your VD will become V1 only. And now we will apply KCL such that this expression is in the form of IF. This IF is incoming and this I is outgoing. IF is equal to I. We will put the value of IF and I here. What is the value of IF? IF is nothing but the reverse saturation current, that is IS into e to the power Vd divided by Vt is equal to, I can say, 0 minus Vo divided by Rf. We can easily get to know that what is Vo? Vo is equal to minus Rf multiplied by Is into e to the power Vd divided by Vt. That gives you the expression of anti-log amplifier. In log amplifier we have got ln, and in anti-log amplifier inverse of ln, that is nothing but e to the power something, and that e to the power something I can easily convert it into 10 to the power something by just mathematical expression. This is your expression which is expected as the expression for anti-log amplifier. Now this anti-log amplifier is doing the job exactly reverse to that of your log amplifier. Log amplifier is doing the dynamic compression, right? And the anti-log amplifier is increasing exponentially. The value which is increasing exponentially, that job is done by anti-log amplifier. We can easily convert this particular issue of temperature dependency by using 4 operational amplifier. One is with V1, one is with VREF, one is with differential amplifier, and another is with buffer circuit, such that we are getting exactly same this expression but excluding the parameter Is, which is dependent on the temperature. So our expression will be not dependent on the temperature. Rather than that, we will be getting the expression as Vo is equal to minus VREF, which is perfectly DC value, into e to the power Vd, that is nothing but V1 divided by Vt. That will be your expression for anti-log amplifier. I hope you have learned a lot in log amplifier and anti-log amplifier session of this particular video. If you like this video, like, share, comment and subscribe Ekeeda channel. Thank you very much.